Now I would like to introduce another structure of the distribution called congruence. In nonparametric statistics, a very often test is that a nonparametric test is, for example, there are two different groups. This is the corresponding distribution. The skewness decreases and the mean increases, also the variance increases. And then often we want to use some nonparametric test to test that whether whether the mean location increase, the scale, or whether the scale increase, the skewness increase. It is like that. But and normally we don't care about the exact value of the. For example, if you use the medium, you normally don't care what the medium is. You just care about whether using the medium can test it. There is a differences. So this principle, indeed, it has an implication that when there is a shift, if we assuming these two distributions are from the same larger family of distribution, and this assume is valid because theoretically, if you want to compare two groups, and normally these two groups normally share some similarities, it should not be completely different. Otherwise, you may not want to compare it, right? So if when there is a shift in the parameters of the underlying distribution, all nonparametric estimates should asymptotically change in the same direction, and if they are estimating the same attribute of this distribution. So and for example, if this principle is not valid, for example, if the mean increases and then the median decreases, and then what we can suggest, and these two parametric tests will produce contradictory results. However, very surprisingly, that such contradiction is possible. You just consider very common distribution, the Weibull distribution. If you consider alpha equal to 1, and then the median is close to 0.693, and then the mean is equal to 1. If alpha is equal to 1/2, and then the median is equal to 0.48, the median decreases, but the mean become 2, it increases. So in such cases, this already say that there is a fundamental flaw in nonparametric statistics. So this is why we should embrace semiparametric statistics. And we previously we already demonstrated that we can classify semiparametric distributions using the science of derivatives, and in order to avoid such scenarios, and we can also use the quantile average, consider the partial derivative of the quantile average with respect to alpha, and then if this partial derivative is always positive or always negative, and then this distribution is called congruent, gamma congruent, and a distribution is completely congruent if and only if it is gamma congruent, and all its central moment current distributions is also congruent. Indeed, I consider this congruence is because later I want to consider estimating using the mean and the median or other trim mean using other location estimator to estimate the central moment kernel distribution. So this question naturally arises, and also an asymmetric, and then we find defining some theorems, but much less than the ordinaries. We can just until now I can just find that symmetric distribution has a nice property, and also positive defined location scale distribution is always gamma congruent, but for some common parametric distributions besides the Weibull distribution, others are generally congruent. And for this Weibull distribution, the reason that it is non-congruent is that because when the parameter changes, generally the values are close to 0 and close to infinity. They both the probability density both increases, but the values close to medium, it will decrease. So this is why that the medium and the means will return very different results. And although some parametric distributions are not congruent, but remember that previously already discussed that a positive defined location scale distribution is always congruent, and also the second central moment kernel distribution from a location scale unimodal distribution, and therefore it is also congruent. And also we demonstrated that they are all central moment kernel distributions from a unimodal distribution are all unimodal-like with mode and medium close to 0. And so if we're assuming that they are bounded distribution, if we're assuming the maximum and the minimum values are the same, and then we consider when the central moment current distribution changes, when the mean increasing. So how to increase the mean? The only way is increasing the probability density on the tail, right? It will like this. And because the medium doesn't change, the medium is always close to 0. We assume it to be 0, so the probability density near the medium, it will decrease. So in this way, such changes will naturally increase nearly all symmetric weighted average. You can see in this way. So that means the central moment kernel distributions generated from the unimodal distribution, it not only holds the very elegant property that it is nearly unimodal with mean and mode close to 0, but also it is nearly congruent, and this is